Hello everyone, my name is Benjamin Munji and I am going to be taking you through my final presentation for my final AI project, Sephora the AI pharmacy assistant. And let us dive right in. The background of this project was that we were supposed to develop a knowledge-grounded pharmaceutical large language model to serve as a decision support assistant for rural drug shops and clinics in Uganda, where trained pharmacists are scarce. Dispensing is often done by semi-skilled workers, and antimicrobial resistance is a growing threat. And so the problem statements, we have a domain application problem, which is drug dispensing, antimicrobial resistance, semi-skilled drug shop attendants, and limited digital infrastructure. Then a computational problem, recommend safe drugs, prevent misuse of antimicrobials, support semi-pharmacist dispensers, and improve patient safety. So the related works were very many, but we had put those that could fit. We have Musoke D and all, health approach to strengthening antimicrobial stewardship in Wakiso district in Uganda. The model was a multi-sector health antimicrobial stewardship training and community engagement in Wakiso, and the key results were they reported improved antimicrobial stewardship practice, self-reports among health practitioners and community workers, reduction in some unnecessary use after training. Then the second was Chigundu R and all, development and evaluation of a continuous quality improvement program for antimicrobial stewardship in 6 hospitals in Uganda. Continuous quality improvement implementation of antimicrobial stewardship bundles in 6 hospitals. Then the key results were improved appropriate antibiotic use metrics. The research questions and objectives, we formulated some and these are some of them. How can AI support safe drug dispensing in rural Uganda? Can large language models plus knowledge graphs reduce errors and antimicrobial risk? How do we design for low resource setting? How can recommendations be made explainable and guideline based? And then the objectives were build a knowledge grounded large language model with local guidelines like the Uganda, like guidelines from the Uganda, the Ministry of Health, and so the objectives were supposed to build a large language model using local guidelines, like the guidelines provided by the Ministry of Health and the Uganda Drug Institute, and then model a drug knowledge graph based on interactions and rules, then implement a RAG pipeline that is safe and explainable, and then evaluate vast pharmacies. So the research contributions were we created a clinical large language model that uses Uganda's guidelines. Then we built our first KG for Uganda. We deployed a RAG and KG reasoning pipeline, and then we evaluated vast pharmacies. The methodology and system architecture. The system works in 3 main stages: data processing, knowledge graph construction, and retrieval augmented generation, which is RAG. The first one, which is the data processing, it starts with raw medication data. Then we sort the data. The key sections are identified, like dosage, side effects, interactions, notes, and advice, and then it's transformed into a structured format, which prepares the data for graph construction. Then when we're building a knowledge graph, the processed data is stored in a Neo4j, as you can see, which represents information as nodes, i.e. entities such as drugs and diseases, and relationships like connections such as treats and interacts with. Then the embeddings models generate two types of representations: semantic embeddings and structural embeddings. The semantic embeddings capture the meaning of the content, and the structural embeddings show how entities are connected to the graph. Together, these embeddings give the system both the contextual understanding and the relational structure. Then the RAG, when a user query arrives, the large language models are used alongside embedding models. The query is converted into an embedding and compared with the embedding indexes using similarity search to find the most relevant knowledge from the graph. The retrieved information is then passed back to the large language model, which uses it to generate a precise, context-aware answer. Then the model architecture. In the model architecture, our chatbot uses a transformer-based architecture similar to BART, fine-tuned for intent classification. User text is first tokenized into subwords and converted into embeddings with positional encodings added to preserve word order. The transformer encoder, a stack of self-attention and feed-forward layers, processes all tokens in parallel, so each word understands its context with the whole sentence. A special CLS token summarizes the entire message. That summary vector passes through a classification layer that outputs probabilities for each intent. During training, the model learns to minimize cross-entropy loss, improving its ability to predict the correct intent. Finally, the predicted intent maps to predefined chat response. Then the mathematical foundations of the model, it was built on attention mechanism, which lets every word in a sentence focus on all other words to understand meaning in context. It learns contextual embeddings, so the meaning of the word like dose changes depending on surrounding words such as paracetamol or ibuprofen. The model was first pre-trained on large text corpora using mass language modeling, then fine-tuned on our labeled intent data to adapt to the medical domain. Training uses gradient descent and cross-entropy loss to adjust millions of parameters to the model correctly predicts. So the model correctly predicts the most likely intent for each input. So the dataset description, basically the dataset was, we had hundreds of datasets. We had very many datasets, but all the datasets were containing a drug. But if we quickly learned that most drugs in Uganda do not have so many drugs, say hundreds of drugs per disease, it has like a few, at most 10, 15. So we collected as many drugs, and so our aim was to make the AI model more intelligent and better at predicting. We were supposed to pick another strategy, which was to increase the training examples for the model. Our dataset had 284 rows and 27 columns. So here we see the distribution of missing values in the chatbot dataset. There's not much to say. And then here we have the chatbot tags distribution. We have the frequency versus the guideline status. And then the evaluation metrics, we use accuracy, precision, recall, F1 score. Accuracy, the proportion of correctly predicted positive instances out of all instances predicted as positive. And it is best used when the class distribution is balanced. It gives a good overall sense of performance, but can be misleading with imbalanced datasets. Precision, a proportion of correctly predicted positive instances out of all instances predicted as positive. It's crucial when the cost of a false positive is high. Then recall, a proportion of correctly predicted positive instances out of all actual instances. Then it is crucial when the cost of a false negative is high. F1 score is the harmonic mean of precision and recall. It provides a single score that balances both concerns. Best used when you need a balance between precision and recall and when the class distribution is balanced. It is more informative than accuracy in such cases. So the model comparison, we had so many models that we have not included here. We tried so many simpler models, and then we were advised to opt for a more complex model. And so we had started with FLAN T5 because it has free-form text generation, open-ended dialogue, explanation, summarization. It may hallucinate and generate unsupported dosing, but everything has risks. And the training it needs careful prompt design and fine-tuning to constraint inputs. It was, it, I can't say it really worked out. It did not come help us so much, so we had to go for, we sought advice and we went for BAT because the flanks, as you can see here in the, I don't know if I can zoom in. Here, it was not really improving enough after 14 epochs. The evaluation metrics were still poor. Loss hadn't dropped below 3.75, and accuracy still stuck low. Good training graphs usually shows steeper decline in loss. And then we sought advice from a senior, and they advised us to use BAT. Um, sorry. But which scores, it gives scores for predefined classes like drug dose guidance, but it's used in classification ranking and structured prediction. And as you can see, the results were pretty good. The results were pretty good. The accuracy, overall predictions were pretty solid for a 7-class task. And it was good. The F1 score was also very good. And then the precision was also good. Generally, we got much better results. We tried the model like 3 times with different ways, but with each try, it kept giving us better improvements. And so this is not really the final try, but it was one of the tries that gave us very good improvements. And we hope by the next, we hope to keep improving it. I think we shall be improving it. We can't really improve it with data because in order to expand our data set, we'll have to increase the number of drugs. But increasing the number of drugs does not really help it predict better as a particular drug. For example, even if we had one drug, malaria, and we added typhoid, we added dysentery, it's really not going to help that AI predict better malaria. or when it's not going to help it predict better at those. So we needed to find other smarter ways, like improving the training examples. That's one way we could help. And yeah. So in conclusion, our AI can, we believe our AI can improve self-dispensing in rural Uganda, and the combination of large language model and knowledge graph is explainable. Gives explainable guideline-based recommendations, and it can help reduce errors and antimicrobial resistance, which was the main point. And we added we added a special feature that can help it be used offline, because not Uganda has very many inaccessible areas in terms of internet connection, so we had to account for that too. And so we came across some limitations, and as I said earlier, we had limited data, which was few digitized prescriptions. That Yes, we had actually a problem of few digitized prescriptions, and we had to contact actual pharmacists, and we had to look really deep. We had to form our own data set, in fact, because most of the most of the content on the internet about Uganda medicine was outdated. 2007, one article about the guideline, the medicines was 2007. So we had to contact a few pharmacists and contact people who with authority in that area, and maybe make some little research in order to form our data set. And then we had model hallucinations. The language model can give unsafe advice, but obviously with more training and more work, we can improve that. That is not really something that we should look at as a big deal. And so even the internet connection, like I said, we have solved it by producing a lightweight model, and that can be deployed offline. And I guess that is it. That's just about it. And I would like to acknowledge the Almighty for helping us through all this. It was really tough and challenging. I would like to thank our lecturer who enabled us embark on this eye-opening journey that helped us rekindle our love for research, our love for software engineering. I'd like to thank myself for not giving up, because it has been really a very demanding task. It was very demanding, and both physically, mentally. Yeah. Thank you so much, and have a nice day.